Hello everyone, welcome to Avalanche Breakdown YouTube channel. So let's discuss about another sensor. It's called radar. Radar stands for radio detection and ranging. So what are the things that we'll be discussing here in this document? What is radar, meaning of radar, why radar is important in autonomous driving, electromagnetic wave fundamentals, basic radar working principle, radar object detection, and summary. So let's start to discuss. So first of all, what is radar? Radar is an active sensing technology that uses electromagnetic waves to detect objects and estimate their distance, relative velocity, direction, and sometimes size or shape. A radar sensor transmits electromagnetic wave towards the environment. When the transmitted wave encounters an object, a part of the energy is reflected towards the sensor. The returned sensor is called as an echo. By processing this echo, the radar can determine how far away the object is, whether the object is moving, how fast is it approaching or moving away, the horizontal direction of the object. In advanced radar systems, the elevation and approximate shape of the object can also be found out. Radar is an active sensor because it produces and transmits its own electromagnetic energy. It does not depend entirely on sunlight or external illumination. Radar is a sensing system that transmits electromagnetic waves and analyzes their reflections to detect objects and estimate their range, velocity, and direction. A basic radar system operates as follows. Electromagnetic signal transmitted. Signal travels through the environment. Signal strikes an object. Part of the signal is reflected. Radar receives the echo. Signal processing algorithms analyze the echo. Object range, velocity, and direction are estimated. Here one thing to understand is that radar is very good at understanding the velocity of the object, but it is not very good to understand what is the shape of the object. So in order to understand what the shape is, many a number of times it is actually the data of radar is fused with other sensors. Automotive radar is widely used in ACC, adaptive cruise control, automatic emergency braking, forward collision warning, blind spot detection, lane change assistance, rear cross traffic alert, parking assistance, highway driving, autonomous navigation. Meaning of radar. The word radar stands for radio detection and ranging. The name describes fundamental purpose of the technology, radio. It uses radio frequency electromagnetic waves. Detection. It determines whether object is present. Ranging. It calculates the distance between the radar and the object. Modern automotive radar does more than ranging. It can also estimate relative velocity, azimuth angle, elevation angle, signal strength, object confidence, object dimensions, motion state. Automotive radar commonly operates around 76 to 81 GHz frequency range. These high frequency waves are suitable for compact antennas and high resolution distance measurements. Next, let's talk about the next topic. Why radar is important in autonomous driving. Radar is one of the most important sensors in autonomous driving because it provides reliable distance and vehicle velocity measurements under conditions where cameras and LiDAR may perform poorly. A camera provides rich color and semantic information while LiDAR provides accurate 3D geometry. Radar adds highly reliable relative velocity measurement and strong performance in adverse weather. Direct velocity measurement. One of the radar's greatest advantages is its ability to directly estimate the relative velocity of an object using Doppler effect. For example, a front radar can determine whether another vehicle is moving towards the ego vehicle, moving away, traveling at the same speed, suddenly slowing down, or cutting into the lane. This is what direct velocity by the radar can be measured. Camera and LiDAR systems generally estimate velocity by comparing object position across multiple frames. Radar can measure radial velocity directly from returned electromagnetic signal. Operation in poor lighting. Radar does not depend on visible light. It can operate during day, night, bright sunlight, shadows, tunnel entry, exit, headlight glare. Better performance in adverse weather. Radar waves are generally less affected than visible light by fog, rain, dust, smoke. Radar performance can still degrade in severe weather, but it normally remains more useful than a standard RGB camera in such conditions. Long-range automotive radar can detect vehicles at substantial distances, making it useful for highway driving, adaptive cruise control, early collision warning, high-speed emergency braking. Accurate. This is very important. Next, accurate time to collision estimate. Radar provides both range and relative velocity. It is very important line. It cannot understand what the object actually looks like, but it can actually tell what is the velocity of the object which is in front of it. These values can be used to estimate time to collision or TTC. A simplified equation is TTC is equal to d by ER, where d is the distance to the object and VR is the closing relative velocity. It allows the object to determine how urgently braking or evasion action may be required. That's why what we actually do is we keep radar in all the directions across the means around the vehicle, so that we get to know in case suppose a car is going in a lane, and if we have radars around the vehicle, then we can get to know if uh, the vehicle is actually crossing onto our lane. Okay. Support sensor redundancy. Autonomous vehicle require more than one sensing method. Radar provides an independent source of information that can validate or complement camera and LiDAR observations. For example, camera identifies an object as a vehicle. LiDAR measures its 3D geometry. Radar measures its relative velocity. Sensor fusion combines all the three measurements. Main advantages of radar: direct relative velocity measurements, long distance range, reliable day and night operation, good adverse weather performance, low dependence on visual appearance, effective detection of metallic objects, relative compact hardware, mature automotive technology. Main limitation: lower spatial resolution than camera and LiDAR, sparse measurement, difficult object classification, multipath reflection, ghost objects, poor elevation resolution in conventional LiDAR, difficulty distinguishing closely spaced objects, strong reflection from metal surfaces, limited ability to detect object color and texture. For these reasons, radar is normally used together with cameras, LiDAR, IMU GNSS and wheel speed sensors. As we discussed earlier, what happens is like sensor fusion plays a very important role. Instead of using just one sensor, it is better to use different sensors together. Next, let's talk about electromagnetic wave fundamentals. What is electromagnetic wave? An electromagnetic wave is a form of energy that travels through space as changing electric and magnetic fields. It consists of electric field, magnetic field, direction of propagation. The electric and magnetic field oscillate perpendicular to each other and perpendicular to the direction in which the wave travels. For example, this is what it is: wave propagation, electric field, and you have magnetic field. Magnetic field extends perpendicular to both. Electromagnetic waves do not require a physical medium. It can travel through air, vacuum and certain materials. In a vacuum, electromagnetic waves can travel at the speed of 3 into 10 power 8 meter per second. Important electromagnetic wave properties include frequency, wavelength, amplitude, phase, polarization, propagation, speed, power. Frequency and wavelength are related by c is equal to nu f lambda, where f is the speed of c is the speed of light, f is frequency, lambda is the wavelength. Therefore, lambda is equal to c by f. Higher frequency correspond to a shorter wavelength. Electromagnetic spectrum. The electromagnetic spectrum is complete range of electromagnetic radiation arranged according to the frequency or wavelength. Low frequency, long wavelength, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Okay, these are low frequency to wavelength, and then at the end you have high frequency and short wavelength. Different parts of the spectrum are used for different applications. Like radio waves are used for communication and broadcasting, microwaves are used for radar, satellite communication, wireless networks, infrared for thermal imaging, remote control and LiDAR. Visible are used in cameras, ultraviolet, inspection and sterilization, X-rays, medical and industrial imaging, gamma rays, medical treatment and nuclear research. Automotive radar operates in microwave or milliwave region. Right. Next, let's talk about radio waves. Radio waves are electromagnetic waves with frequency lower than infrared radiation. They are widely used for wireless communication, broadcasting, navigation and radar. Radar systems use high frequency radio waves because they can travel rapidly through air, reflect from objects, carry phase and frequency information, penetrate fog, dust and certain weather conditions better than visible light, be generated and measured electronically. An automotive radar commonly uses milliwaves around 77 GHz. At 77 GHz, lambda is equal to 3 into 10 power 8 by 77 into 10 power 9, 3.5 mm. This short wavelength enable compact antenna arrays and improved angular resolution. How does a basic radar, what is a basic radar working pipeline, working principle? A radar sensor detects objects through sequence of signal transmission and signal processing operations. The complete process is waveform generation, signal transmission, wave propagation, reflection from objects, echo reception, analog signal condition, analog to digital conversion, range Doppler angle processing, object detection, clustering and tracking. Signal transmission. The radar transmitter generates an electromagnetic signal and sends it through one or more transmitting antennas. Automotive radar often uses FMCW or signals. FMCW radar The transmitted frequency increases or decreases over a short period. The frequency sweep is called as chirp. What here we are seeing is like this with frequency and time. This is how it changes. One chirp, right? The transmitted frequency increases or decreases over a short period. This frequency sweep is called chirp. This is one chirp. Important transmission parameters include start frequency, end frequency, bandwidth, chirp duration, chirp slope, number of chirps, transmit power, and antenna pattern propagation. After transmission, the electromagnetic wave travels through the environment at approximately the speed of light. During the propagation, the signal may experience free space power loss, atmospheric absorption, scattering, reflection, diffraction, interference, multipath propagation. The received signal becomes weaker as distance increased. A simple relation is that return power decreases rapidly with increasing range. As a result, detecting a distant object requires sensitive receivers and advanced signal processing. Reflection. When a radar wave reaches an object, the part of a signal is reflected towards the sensor. The strength of the reflection depends on object material, object type, object shape, surface orientation, frequency, distance, angle of incidence, radar cross section. This thing is very, very important, and we will discuss about it later in this document. And this is what it is, the next section. Large metal usually produces stronger return than a small pedestrian. What is radar cross section? Radar cross section, or RCS, describes how strongly the object reflects radar energy towards the sensor. RCS is expressed in square meters or decibels relative to 1 square meter, written in dBsm. Objects with larger RCS values are generally easier to detect. However, RCS does not equal physical size. A smaller metal object may sometimes return more energy than a larger object made from weakly reflective material. So it basically depends on what kind of material you are using. So different kinds of material will have different RCS. Sometimes a stealth aircraft which has been made using stealthy materials will have RCS similar to that of a very small bird. So that is what this stealthy technology is all about. Echo reception. The reflected signal returns to the radar and is captured by receiving antennas. The received echo is normally much weaker than the transmitted signal, delayed in time, shifted in frequency, different in phase across different antennas. These differences contain information needed to calculate range, velocity, direction. The receiver commonly contains receiver antenna, low noise amplifier, mixer, filters, analog to digital converter. Signal processing. The received signal is mixed with a copy of transmitted signal. This produces a lower frequency signal called the beat signal, intermediate frequency signal, IF signal. The beat signal is sampled using an analog to digital converter. The digital signal processing then performs operations such as windowing, range FFT, Doppler FFT, angle estimation, CFR detection, clustering, object tracking. So all these are signal processing techniques for radar signal. Simplified pipeline: raw ADC samples, range FFT, range bins, Doppler FFT, range Doppler map, angle estimation, radar detection, clustering and tracking. Next, let's talk about distance measurement. Distance is estimated from the time delay or frequency difference between the transmitted and received signals. For pulse radar, R is equal to C into del T by 2. All these are actually variations of speed is equal to distance by time. That's all. Where R is object range, C is the speed of light, and delta T is the round trip travel time. The division by 2 is required because signal travels from the sensor to the object and then back. In FMCW radar, the distance is commonly estimated from the beat frequency. R is equal to C into FB by 2S, where R is the range, FB is the beat frequency, S is the chirp slope, C is the speed of light. The chirp slope is S is equal to B by TC, where B is chip bandwidth, TC is chip duration. Velocity measurement. Radar measures radial velocity using Doppler effect. When the object moves relative to the radar, the frequency of the return signal changes. An approaching object produces one direction of frequency shift, a receding object produces the opposite direction. A Doppler frequency can be related to radial velocity by Fd is equal to 2 into Vr by lambda. Therefore, Vr is equal to Fd into lambda by 2, where Fd is the Doppler frequency, Vr is the radial velocity, and lambda is the wavelength. Radial velocity limitation. Radar directly measures only the velocity component along the line between the sensor and the object. For example, object moving sideways across the vehicle path may have high real velocity but low measured radial velocity. This is a very important thing to understand. Angle measurement. The direction of an object is estimated by comparing the phase of the received signal across multiple antennas. When a wave reaches an antenna array from an angle, it reaches each antenna element at a slightly different time and phase. The radar uses these phase differences to estimate azimuth elevation. Azimuth is the horizontal direction of an object relative to the sensor. Elevation. Elevation is the vertical direction of an object relative to the sensor. Common angle estimation techniques include phase comparison, digital beamforming, angle FFT, music, Capon beamforming, MIMO processing. Conventional automotive radar often has good azimuth resolution but limited elevation resolution. Imaging and 4D radar systems improve both. Radar object detection is a process of converting reflected electromagnetic signals into meaningful detections representing object in the environment. The basic process is raw radar signal, range and Doppler processing, angle estimation, detection and thresholding, radar points, clustering, object classification. Tracked objects. Radar initially detects reflected signal peaks. These detections do not automatically indicate object type. Additional clustering, tracking, sensor fusion or machine learning algorithms are required to identify vehicles, pedestrians, cyclists and obstacles. One very important thing to understand is that based on the radar cross section we can actually understand what kind of thing it is, but honestly speaking we do not know, and it is not very clear. Just like LiDAR data, only with radar data we cannot tell what kind of object it is. Vehicle detection. Vehicles are generally favorable radar targets because they contain large metallic surfaces that strongly reflect electromagnetic waves. Radar can estimate a vehicle's distance, relative velocity, horizontal position, distance, approximate width, motion state. Vehicles detection is used for adaptive cruise control, automatic emergency braking, cut-in detection, lane change assistance, forward collision warning. What are the challenges? A single vehicle can produce multiple radar reflections from front bumper, wheel, corners, license plate, chassis, other metallic parts. These multiple detections must be grouped into one object. Another challenge occurs when two vehicles are close together. Poor angular resolution may cause them to appear as one object. Object detection. After estimating range, velocity and angle, the radar determines whether each signal peak represents a real object. A common detection algorithm is CFR, which stands for Constant False Alarm Rate. CFR estimates local noise levels and set a detection threshold. Signal. So how does it work? Signal power, local noise estimation, adaptive threshold, signal above threshold, radar detection. Each detection may contain range, azimuth, elevation, radial velocity, signal strength, RCS, confidence, timestamp. Nearby detection may then be grouped into clusters and tracked over time. Now let's talk about radar object detection. Radar object detection is the process of converting reflected electromagnetic signals into meaningful detection representing objects in the environment. The basic process is raw radar signal, range and Doppler processing, angle estimation, detection, thresholding, radar points, clustering, object classification, tracked objects. Radar initially detects reflected signal peaks. These detections do not automatically indicate object type. Additional clustering, tracking, sensor fusion or machine learning algorithms are required to identify vehicle, pedestrian, cycling and obstacles. Vehicle detection. Vehicles are generally favorable radar targets because they contain large metallic surfaces that reflect, this we have seen earlier as well, strongly reflect electromagnetic waves. Radar can estimate a vehicle's distance, relative velocity, horizontal position, direction, approximate width, motion state. Vehicle detection is used for adaptive cruise control, automatic emergency braking, cut-in detection, lane change assistance, forward collision warning. The challenges also we have seen earlier. Now what about pedestrian detection? Pedestrian detection is most difficult because a person has smaller RCS than a vehicle. A pedestrian may produce reflection from torso, arm, legs, personal objects, metallic accessories. Moving arms and legs create small Doppler variation known as micro Doppler signatures. These signatures can help distinguish pedestrian from vehicle or stationary objects. What are the challenges? Weak reflected signal, small physical size, occlusion by vehicles, low radial velocity when moving sideways, complex body motion, reflection from nearby infrastructure. Radar is often used with camera information for reliable pedestrian classification. See, with sensor fusion, the thing is like we can fuse two different sensors to produce meaningful outputs. LiDAR and camera can be fused, radar and camera can be fused, radar, camera, LiDAR, IMU, GNSS, everything can be fused together. So it depends how much redundancy do we want, and it also depends upon the algorithms that we are using and how much accuracy those algorithms are providing us. Static obstacle detection. Static obstacles include parked vehicle, barrier, road debris, guardrails, wall, pothole, construction equipment, stationary pedestrian. Static obstacle detection is most important for autonomous driving, but many traditional automotive radar systems remove stationary reflections to reduce clutter. This can create serious problem. A stationary object in the driving path may be incorrectly filtered out. Modern systems therefore attempt to separate relative static obstacles, roadside infrastructure, ground clutter, multi-path reflection, irrelevant background objects. The ego vehicle's motion must also be considered. A static world object appears to have relative motion when observed from a moving vehicle. So radar sensor fusion pipeline, how does it look like? A typical autonomous driving pipeline is front and corner radar sensors, radar detection, coordinate transformation, ego motion compensation, clustering and tracking, association with camera and LiDAR objects, fused object position and velocity, prediction, planning, vehicle control. So with this we have come to an end. So what is it that we have discussed till now is like radar uses electromagnetic waves to measure object range, radial velocity and direction. It is especially valuable because it measures velocity directly through the Doppler effect. Radar works during the day and night and usually performs better than cameras in adverse conditions. Short, medium and long range radar sensors serve different vehicle functions. Front radar supports ACC, emergency braking, while corner radar supports blind spot and traffic detection. Imaging radar provides improved angular and elevation resolution. Object detection converts signal peak into vehicles, pedestrians, cyclists and obstacles. Tracking estimate object motion continuously across multiple frames. Accurate spatial and temporal calibration is essential for sensor fusion. Radar is strongest when combined with camera, LiDAR, IMU, GNSS and vehicle motion information. As we have seen many times before, it's like the weakness of one sensor can be compensated with the strength of another sensor. That's why it is better to sensor fuse all of them together. So we have completed this radar, radio detection and ranging, and in this chapter we have seen radar, meaning of radar, why radar is important in autonomous driving, electromagnetic wave fundamentals, basic radar working principle, radar object detection, summary. Thank you very much.